do so through the Start menu. If you have your own laptop, presumably you're more familiar than I with how you start it. I too am going to start up AnyLogic here. So here we go. Now AnyLogic, when it starts up, the very initial time, it'll actually be at a special. It'll show you some special content that reflects the fact that you may be interested in learning additional material. And depending whether you've called it up previously, you may see different things. Many of you will see this. If you do see this, I want to highlight it because there's many useful things here. Getting to example models, finding out about features, etc. We have contributed in our lab quite a few health-oriented models together with Jeff here to this set. There's many other types of models, as you can see, that extend well beyond the health domain. Because we are in this boot camp have a particular focus on health, we will not be availing ourselves that frequently of this, but you should know it's an important resource. There's also a set of tutorials that are very helpful in building some skills, which I'd recommend as complements to what we've provided in terms of the step-by-step tutorials. But for this, I'd like to go press this minimize button. AnyLogic has a so-called user interface, a skin, a kind of a set of components that it presents to you to let you interact with it. That takes a little bit of getting used to, and it makes use of kind of these windows which have particular purposes. This welcome window is one you'll occasionally see, but when you close it, you should see something that looks like this. There should be a projects window on the left, and somewhere there should be a properties window, either at the top or bottom. Do you see that? Okay. If you did not, you could go to the View menu and you can choose what things should be shown at any time. So, for example, we'll be making strong use of the palette, and if you were to click here, you should be able to make use of showing the palette here. And AnyLogic can also provide a sort of easy, accessible version there. We're going to actually not need the palette for this first version. The palette is sort of where we pick up the items to be added to the model, so I'm going to close that. We're going to go open this model that we're going to be using this time. Now, in order to do so, we're either going to open it off your thumb drive or download it from the site, okay? So I will show you how to download it from the site. If you're going to open it off your thumb drive, why don't I show that first, just to get people started. I'll do File, Open here, and I'd like you to go to the place on your thumb drive that says AnyLogic 8 models, or AnyLogic 8 examples, okay? There should be a folder that says that on your thumb drive. Do you see that? If any of you feel comfortable doing it, you can go to that URL, materials, and you'll also see a folder there. Okay. If you see that, you could go enter it, and you will see a wide variety of models here. I would like you to scroll down, and there's one called GIS Food and PA, that's physical activity rather than Prince Albert, environment version 4 underbar AnyLogic 8. Do you see that? In this boot camp, we err on the side of descriptive names rather than short names, which is why autocomplete is so useful. Okay, I'd like you to go into that folder, and you will find that there's a so-called ALP file there. This is an AnyLogic file, AnyLogic project file, ALP. So I'd like you to open it. You can do so by double-clicking on it or pressing OK here, and it will load in this file. Now, for those of you operating online, I will now go and show you how you can do the same thing online, okay? If you do this, you could see this model, and you can, for those who have loaded it, you could double click over here, say on person, and go start to explore what's in the model. But let me focus on those who are bereft of access to your thumb drive and require recourse to the website. So I'm going to call up a web browser, and I'm going to enter in the name here for the ABM Bootcamp 2017 and materials. Okay, that's the same URL that's over here in the upper left. Okay. Okay. So having done so, we should go to a Google Drive folder, which stands before us. There's an AnyLogic 8 examples here. Do you see that? Yeah? Okay, so anyone who does not see that? Okay? Okay, double click on AnyLogic 8 examples. You will find a similar set of AnyLogic examples, or a similar set to what we saw on the thumb drive. I would ask that you sort them by name. You can click on name and you will sort them, which would then allow you to go down to GIS and PA environment version 4 AnyLogic 8. Okay? And having done that, I would ask that you double click on this. This process of getting things from the web involves a little bit of finesse and, frankly, a little bit of ugliness. But once you've mastered it, this is a skill you'll probably want to use several times in the boot camp, because remember, I'll be distributing my models that are being built in each session via the same mechanism. And if you want to get my latest version of the model because you've encountered some challenge, you want to use the exact one I'm using, you'll want to go through a similar interface. So we went into the bootcamp folder, and we, in this participants resources, we went into AnyLogic 8 models. We sorted by name. I clicked on name. We went down to GIS, food, and PA environment until we see this ALP file. Do people see that? See that? Who needs a bit more time? Okay. Now, this, ladies and gentlemen, is where the ugly truth begins. Okay? So I'd like you to go and double click on this. And you will see something that is, it lacks complete beauty, but it will be useful. A little bit like me, hopefully. Okay, and here in your browser, you can press download, okay? Over in the upper right, there should be something that says download, and you will press download, okay? And having pressed that, we should get a file on our computer with that same name, ALP. And, well, you'll have to stick with my ugliness for the balance of the week. You could close the ugliness presented here by simply pressing escape, and you'll go back and be free of it. Okay? So this now lies on your computer in your downloads folder. If you're not working with a thumb drive, you can then go and in AnyLogic go open that up. I'm going to go to my downloads folder just so I could demonstrate whither it went. And here we go, downloads, and I'll go and go find that model there. Okay. So it just went and it was placed there, and let me sort it by there, and there it is in my downloads folder, and you could open it and bend it to your will. Okay? You could just open it up by double clicking on it. It will open in AnyLogic. Okay? Are people okay with that? Who needs help? Aiden is distributing updated thumb drives. So perhaps the skills I just taught will not be needed immediately, but they will be skills that you'll want to apply elsewhere. When we distribute additional example models, this may sometimes happen. We'll probably do so through the web. Okay? Okay. Any questions on that process of downloading? We'll be exercising that quite often in the boot camp, so I just wanted to emphasize it. Okay? Okay. Ladies and gentlemen, with that in mind, then, I would like to return our attention to AnyLogic. We loaded in this model, GIS and PA environment, version 4, AnyLogic 8. Okay? Let's go and begin by taking a look at this model at a high level. When you open it, you'll probably see main. Do you see something called main there? Yeah? And what you'll see is nothing other than the fair city of Melbourne. The pleasant environs of the charming Yarra River are in this area, and you'll see that there's actually a map showing thoroughfares coming into Melbourne. And there's also a set of resources placed on this map and geographic locations, many of which are indeed geographically rooted. In fact, all of these. These represent the placements of parks. These represent the placements of resources such as fresh fruit markets, as well as convenience stores. These were provided from GIS, a Geographic Information System, and placed on these maps at their appropriate latitudes and longitudes. And if you go and you double-click on person, you will see that there's an element to the theory of personhood captured within this model. There's sort of a hypothesis what it means to be a person in this model in terms of some salient behaviors. Some of those behaviors involve factors governing their weight. So there's some energy in from energy intake and some energy expenditure over time. And there's a basal level of energy expenditure and energy expenditure via physical activity beyond that basal level. If we scroll to the right here, you'll see that there's some other aspects of evolution of a person's state that are captured in a fashion using what's known as a state chart. So here, a person could be in a state of not seeking food or engaged in food seeking by heading to a convenience store, to a supermarket, engaging in shopping behavior, and transiting back home. We have further, if we scroll down further, we will see that there's a process that's represented in sort of a flowchart fashion. Because it's rather broad in its extent, I'm going to show you an element to the AnyLogic interface. If you go to person and you double click on it, you will see it expand to form the sole window shown. Do you see that? How did I do that? I just double clicked on this tab, and in fact by double clicking again, it toggles back. It goes back to a form where lots of windows are shown. So you can kind of zoom into a window, as it were, by making it full screen by double clicking on the tab there. Okay, the X next to it would close that window if you sought to do so. So here we've articulated a positive decision-making process with respect to these individuals in the model. An individual, when seeking to eat a meal, has a certain decision process that they go through as captured by the state chart. they're making choices as to what they consume according to what's in their larder and according to their preference in terms of shopping. Okay, so whether that person eats, for example, one of those meat pies, which is frequent in Australia, or partake of a dish called in Adelaide a floater, I think, or floaty, or consume something more rich in fresh fruits and vegetables, is something that will be decided by this flowchart. And the flowchart will govern their behavior periodically when they are seeking to consume a meal. So this too is an element of human behavior as represented in the model. And if you scroll up and to the left a bit, you'll find that there's actually some additional attributes of that person. They have a home. Each person has a home, is associated with a home. You'll see that with this little thing here called a parameter. They have a certain preference that's posited for convenience store meals as compared to the healthier fares obtained through fresh fruit and vegetable dishes. And they also have some representation of the current state of their larder. How many convenience store meals they have remaining in their fridge or supermarket meals, and then some record of how many they've eaten, some aspect of their history. So we stop our double clicking. So we've articulated, as it were, a simplified, focused sort of theory of personhood. People evolve in their weight according to certain rules. People evolve in terms of their shopping behavior as articulated by other rules, and in their individual decision making about meal choice according to other rules. They undertake actions like going shopping, consuming a meal, etc. And they do so in an environment that was articulated here in the fair city of Melbourne. Which is viewed as one of the most supportive of physical activity, I believe, in the developed world. Now, this theory of personhood is articulated by this model, and individuals are placed into an environment, but its full implications are not immediately obvious. If we articulate this kind of behavior on the part of an individual, how it leads to changes over time in terms of people's weight is something that is not immediately apparent. We have rules that govern how their weight changes at a given time in relation to what they're eating and the amount of physical activity they're getting, say by association with parts, but its implications for how their weight will change in a trajectory is unclear. How they will interact with others in their vicinity is not fully clear. How the overall health status of the population will evolve. Also, it's hard for us to take this articulated theory, as precise as it is, and turn it into some expectation for the population as a whole. More than that, we may be interested in very particular outcomes. Perhaps we have empirical data relating, for example, a person's weight to their distance that they live from a park or from a supermarket. Or we have some neighborhood level relationships between fresh fruit and vegetable market density and health outcomes. So we'd like to know, does our articulated theory explain these empirical patterns that we see? Or is it consistent with those patterns? Or perhaps our interest is at more of a prescriptive level. We're interested in knowing what sort of interventions in terms of placement of fruit and vegetable markets in erstwhile food deserts would best lessen the disparities we see in terms of prevalence of overweight and obesity in urban lower income neighborhoods versus urban higher income neighborhoods. Perhaps our interest is in asking what if questions. If we were to place supermarkets at certain locations, how would it affect things? If we increase the density of parks, how would that be likely to address things? If we imposed a tax on sugar-sweetened beverages, how might that affect the outcomes in terms of population health? Whatever our questions, it's hard by just this representation, precise as it is, to immediately see the implications. But fortunately, the platform we're working with is more than a modeling platform, allowing us to articulate this theory. It's a simulation platform. It allows us to take that theory and view its logical implications over time in terms of outcomes. So I'd like to invite you to run with me this model for some particular scenarios. And we'll notice some features of it. So I'd like you to take this baseline scenario, and I'd like you to run it. This is a scenario where we have individuals who are engaged in food-seeking behavior. You'll notice these individuals here shown as small, almost bowling pin-like creatures. They live at certain homes. You could see them residing at a home, and periodically they move around. And if you slow it down, and you can slow it down via this button here, you'll notice that their movement actually takes place along streets. They're actually routing themselves through the particulars of the city by the shortest route to a given resource, and they're choosing their destination, it turns out, their convenience store or supermarket, and according to not only their preferences, but the distances involved according to that travel. And those individuals are evolving over time. We're running this model, and you notice we have not just one person, but we have several people, and those people are in this population. If we go and we click on this, do you see this little navigation menu here? And we were to scroll down, you'll notice there's a wide variety of resources here, many of which are associated with particular stores. If we were to scroll down to population here, you have to scroll down a bit. So pull this down, scroll down to population, click on that. What you'll see is, as it were, an enacted version of that theory we articulated. So a given person at the moment has a certain weight. You can see this person's weight is evolving over time. It's evolving towards processes associated with energy and energy expenditure, physical activity. They're also in a given state at a certain time, and that state evolves over time. As their larder is depleted or evolves, they may make a different decision. So here, this individual is someone who has a high propensity for convenience store meals. They've just run out of supermarket meals, and they just purchased a convenience store meal here. And if we were to speed it up, we would note that their behavior is allowing them to partake of an increasing number of convenience store meals over time. They seem to have a high predilection for purchasing. I'm told they don't have corn dogs, or perhaps not pizza pops in Australia, but they have other fares of equal degrees of non-salubrity. So this individual is consuming, but occasionally they'll go to a supermarket and then they'll purchase a whole swack of meals at a single time. You'll notice this is keeping a running count for this individual, the count of supermarket meals eaten versus convenience store meals, and their weights evolving accordingly. Occasionally you'll find them dashing off to go shopping in a convenience store, according to the evolution of their larder. So this is an enacted theory. It's a theory that's being simulated over time to find what its logical consequence is in terms of a given individual's trajectory. And here you could see this individual is encumbered by a growing weight that was growing over time from an initial state to a much higher level of weight. Okay. So here's a particular individual, but we have other individuals in our population. We can scroll up here and we'll see that some individuals are in fact reaching levels of weight that are lower than others. Here's, for example, someone 78 pounds and they have only a slight propensity towards convenience store meals related to the first. So it is as we scroll through these. So we have different individuals stationed in the population. We have a theory of personhood, but it applies to many particular people who differ in their preferences and their location relative to supermarkets, relative to parks, etc. And they are circulating in this environment that exposes them to a certain food environment and a certain physical activity environment. More than that, ladies and gentlemen, we can summarize things at more than the individual level. If we go and we right-click on the screen, we should be able to scroll upwards. So you press the right button down on your mouse, and if you click in these sort of areas, you can drag with the mouse and see things. So up here, you'll notice that we have some figures. For example, this figure relates the fraction of meals eaten at convenience stores on the one hand. So a given person is a dot here. The presence of this dot at, say, 0.07 indicates that this individual eats approximately 7% of their meals at a convenience store. Okay? The y-axis indicates their weight here. Okay? So this particular individual is someone who eats a low fraction of convenience store meals and has a smaller weight. There's individuals who eat larger fractions. For example, this one here eats approximately 40% of their meals from a convenience store, and they have a weight upwards of 100 kilograms. Now, where did that weight come from? Did we put that into the model? Well, we put in an initial weight for them, but their weight evolution following that was an emergent feature of their situation. How far they live from grocery stores, how far they live from convenience stores, their proximity to a park, their decision-making preferences. That's what led them to evolve a certain level of weight. And the fraction of meals eaten at convenience stores is a reflection, yes, of their preferences, but also their situated location, where they are relative to these resources, and if they're a further distance from a supermarket, it may further their propensity to engage in convenience store consumption. So here we have a summary graph that's summarizing the characteristics of many individuals. And one of the things you'll notice is, perhaps not surprisingly, an association. There's an association here between eating meals at convenience stores on the one hand and weight. And it's not quite perfect, it's not quite linear, it's a little bit noisy and so on. As we add more people to the population, we probably see the breadth of it with greater clarity. But it does indicate that broadly, as one eats larger fraction meals at convenience stores, there is a higher weight attained. Let's scroll up some more. Here we have a relationship between the distance of a given individual from a convenience store on the one hand, from a grocery store on the one hand, and their weight on the other. And once again, the graph is a bit noisy. We see that there are some individuals at long distance from a grocery store, but whose weight is not super high. And we see some individuals who are at moderate distance with a quite high weight that's indicated. But this again is capturing some associations from individuals over time. Here we have a ratio between their distance of their home, their domicile to a convenience store versus to a grocery store. So a higher one will indicate that a grocery store is further away than a convenience store, and the weight is on the y-axis. And you'll notice again a somewhat general trend upwards here, although it is quite noisy. And yet another graph associated with preference for meals for convenience stores versus their weight. And we see that people have a greater predilection for, a greater hankering for convenience stores to have a higher weight. And then park distance we could look at as well. So this is a model where we have things going on at an individual level. We have each individual evolving to our theory of personhood, but we further have these statistics about the population as a whole, or summary statistics across the population, or graphs that show for a collection of people their characteristics over time. And that allows us to get some sense of the population level outcomes associated with these individuals. Yes, question?
So, yeah, going back to the graphs.
Yeah.
So in a way, I can understand when you build the model.
Yep.
You build it such that somehow, if you go to a convenience store,
Yep.
that person, that agent, will gain weight. So it's built in. So when you look at that relationship,
Yeah.
you shouldn't be surprised that you find those relationships.
Okay.
So that's when I'm getting confused. It's built in
Okay.
when you're checking.
So I love your point here, and I'd like to have a bit of a discussion about that, because at a certain level you could state, and I don't dispute it, that there is a relationship implied by this model, that it logically follows the assumptions of this model that there will be a positive association between preference for a convenience store on the one hand and weight on the other. That in some sense the model presupposes, you might say, I'm trying to put it in sort of as strong a way as I could, that there's a relationship here. And I would say from a certain distance that would be an accurate statement. But what I would say is that if there is a presupposition, it is a presupposition in the form of a myriad of different assumptions that that make the strength of that association not so immediately clear, and make the implications in terms of the quantitative outcomes incompletely clear. I would further note that there is a set of pathways by which that mediate and in some cases moderate the strength of that association in the form of the physical environment in which they're located. For example, their proximity to parks may lead them to engage in physical activity, which mitigates some of the impacts of their propensity for convenience store meals. The higher their weight becomes, the higher the level of energy expenditure becomes. So there's some feedbacks associated with that. There are further aspects of their decision making that consider other factors besides their strict preference. So here they have a preference for convenience store meals, but if you look at their actual decision-making mechanism within this model, we actually see that their likelihood of, as we say, shopping wisely is reflective of much more than their preferences. This probability of shopping wisely considers as well their distance to the convenience store and their distance to a grocery store. So while they may have a preference, that too is limited and moderated by distances in which they're located. And those distances could be things which are very materially altered if we were to undertake, say, an intervention, right? If we were to place very deliberately convenience stores, supermarkets with fresh fruits and vegetables in food deserts areas of a city. You might find there's some pre-existing association between individuals in lower income areas of the city who have grown up with a diet which has been shaped by the high density of convenience stores around them, and which predisposes them towards higher levels of weight. But if we started to put in place interventions that would focus on individuals who have a high amount of propensity, or they're located in environments and neighborhoods that have a high density of convenience stores, we might counteract that. How those interventions would play out in terms of the associations and how quickly they would play out, whether it's over a 5-year period, a 3-year period, we'd expect to see big lessening of this association we just saw, is not entirely clear. And with a model like this, as we'll talk about in the next lecture, we often have a chance to quantitatively assess, because we have an operational theory of the world that we can run, we can quantitatively assess the degree to which it explains certain patterns we see in the world that are very quantitative in nature, certain associations. Or alternatively, we can use it as an evaluation vehicle for certain interventions for which we don't have data, which are counterfactual in nature. We don't have data on their outcomes. And we want to ask what-if questions that are not, where the data is lacking, and where we want to examine a situation which would be expensive, time-consuming, ethically infeasible to examine in the short term. So in short, a model like this can help us ask, is this theory that we see, this quite articulated theory with these mediating and moderating variables and so on, is that theory is that consistent with the evidence that we see? And it can help us ask, if we undertook some interventions that change the current situation, how would that affect things? How quickly would it affect things? How much would it affect things? To what degree would it blunt this association we see? Would it bend the curve that we just saw in terms of those associations? How much would it bend the curve? These are questions that we can pursue with a model that are not entirely obvious from just articulating the theory. And often we, as people, we're handicapped in a very serious way to take a theory that's in our heads and translate it into quantitative outcomes. And a model provides a way of doing that. You can say, yes, it's all presupposed by the model, and I don't disagree, but it's presupposed by such a complex interaction of factors that we need a simulation tool to understand its logical implications. We're never going to be able to purely see that in our heads. Does that make sense? Yeah. And it's especially, though, when we're dealing with counterfactuals, where we have complex sets of factors that they affect. The location of parks and supermarkets and preferences, and how preferences evolve over time following exposure to foods, that we really need recourse to something that will add up the assumptions here and tell us what the logical implications are. So while I'll say that this, in some sense, presupposes a certain theory, whether or not that theory is consistent with evidence and how things would change in the event of an intervention, that's something we need a simulation for to really gain confident, deep understanding and to be able to evolve our theories of the world. I don't know if that's all. Okay, other questions about this? I welcome these questions. These are great. Others? Okay, so I'd like to take a look at a little bit more of the theory behind this sort of modeling, and talk a little bit about its implications. I would note that, and I would encourage you to explore this, that those who are seeking a more hands-on experience, I would encourage you to engage in problem behavior with this model. So you can run particular scenarios here, as we just did. How did we run that scenario? Let's just rehearse it in case any of you would like to do so. I'm going to stop this model. We can stop it in several ways. Like most things in AnyLogic, we have several options. We could close it here. We can terminate it from this console window. Okay. And having terminated that particular run, we could start up others. You'll notice that down here in the lower part of these pieces of the model, this is depicting pieces of this model. So there's a piece associated with theory of personhood. There's a piece associated with what a supermarket contains or convenience stores. There's a piece that is associated with the homes in which people live or the environment in which people circulate. Most of those are very simple in this model, although the environment has richer sides. But down here in these little X's, the X stands for experiment, okay? And the experiments indicate scenarios that can be investigated using this model, okay? We separate those out from the model so that we can run the same underlying theory of the world with different particular assumptions. We can run it with an assumption, for example, of no impact of physical activity. And if we go click on baseline, you'll notice that here we have disabled the effects of physical activity. Here, baseline with walks, if we click that, we'll find it's the same, but physical activity in this version of the model is actually enabled, okay? There's actually a representation of how physical activity changes, how it affects a person. And we could run that. How would we run it? We'd do so by right-clicking on this and pressing run. And we could see individuals circulating now in this environment and go up and look at the graphs that are etched out above. And we might notice there's some rather different patterns associated that come out when you have physical activity on compared to physical activity off. You'll notice, amongst other things, a larger spread on some of these graphs with physical activity, reflecting the fact that we have parks contributing to outcomes in notable ways, not merely the food environment. So there's a set of different scenarios. Some of them involve a larger population. Bear in mind that when we run this model, what's going on is actually quite intensive. It's looking for the very particulars of Melbourne, where the nearest store is, where the nearest park is, routing them to that according to the thoroughfares that are available. And it's assessing that distance using the actual distance along the streets or the footpaths or whatever you suggest as kind of the appropriate routing mechanism. And so there's a lot of work going on. It actually needs to load some data from GIS servers to sort of relate these factors to this particular environment. So bear in mind that with really large populations, it's going to take a while to run here. But some of you may want to do that. Well, I talk some about the broader environment or the broader theory behind these sort of models. So if you'd like to explore this more, you can do so. Yes, question?
So is that real time? Is it pulling from the cloud and includes in traffic, or is it static, holding a map?
No, it is real time. So it's, in fact, I'll show you. There's a caveat to what I'll say that I'll come back to in just a moment. But if you were to go run this, and I'll do it for a somewhat larger population here. One of the reasons that it runs a little bit slower here is, particularly at the beginning, is do you see this thing where it says running and there's this little kind of down thing? It's actually loading things in from a GIS server to figure out the distance from every one of these little houses to parks and to convenience stores and grocery stores, and using that to affect the decision making of that particular individual. And in that particular circumstance. And in order to do that, it has to request a lot of information from these servers. And so this is indicating network traffic that it's going and obtaining this information to consider it. Now, what you'll notice is that after a time, the needs here are lessened. And there's a reason for that. The reason has to do with, amongst other things, that individuals here are located at a fixed set of homes, and those homes don't actually change over the course of the simulation. So once it's figured out, which parks are closest to this home, which supermarkets to that particular home, which convenience stores to that particular home, it doesn't have to do it on an ongoing basis every time. And so it can, as we say, cache that sort of information. So here it's simulating up to 5 years here, and actually, excuse me, this the time unit of this is days, but over time you'll find it starts to become faster because more and more of the information is already obtained. So there is real-time delivery of this information from online servers, and in fact, if you were to we'll have a bit of a GIS module in this class, but if you were to go click on the map here, and I mention this because I know a few of the projects are shaped, you'll notice that when you click on things in AnyLogic, you'll see information about them in the properties window. And here you'll see, for example, you can select, okay, where do you want to get your routes from an AnyLogic server or from other servers. The AnyLogic one is encrypted. Do you want to use the shortest or the fastest route, for example? Are people going via car, bike, rail, etc.? So there's a lot of assumptions that are specified by the properties associated with this GIS map. Okay, and those underlie the sorts of behavior that we see here. So which server it's going to download information, that's set by this. We can also do things that are more advanced, like specify certain GIS shape files, have a sort of centering of the map, etc. And if there's interest from people in the audience, we could have a session led by a TA, probably a breakout session, where we actually build the first part of a model like this up from scratch, and we situate things in space, and we center it in a different zone, perhaps Cabri Provincial Park, right? And we could have agents circulating in space or have other resources within space. So if there's an interest in that, I'd be glad to ask a TA to hold a session like that in the next day or so, where you could do something like that. Other questions? Okay. Buzzing, looming, confusion. Lots going on here. Let's go, and we're going to have a short break, and we will then take a look at why we build these models. Try to address a little bit some of these great questions that we're getting about. What do these models give us? What new things do they bring to the table? Where do they fit in to the rich toolbox of health system, of health sciences, analytic techniques that are already there? Okay, so I think what I'll ask is if we could keep the break till to 10 minutes, that will be good. And we'll come back and we'll initiate this lecture associated with a background. We will be breaking early today for the eclipse, and that necessitates a bit of a compression this morning. So I appreciate your willingness to bear with that. Thanks very much.
Does anyone need one of these fans loaded up?
How you doing?
Oh, not bad. We're going through and we're trying all sorts of things right now to try to get things up and running.
Okay.
So
Okay.
you're not using this at all?